start with the topic, which is just review of probability theory concepts for the first half, and then discussion of random matrices and random vectors, which we're going to use throughout the course. So it's like the random part, like review of random stuff, let's say. Okay, so I'm going to start with random variables and basic definitions. So a random variable is, I'm hoping most of you know what a random variable is. Just informally, it's a random number, and it's the result of some experiment. So for example, if you do the midterm, I look at the exam pile and just draw one exam at random. The grade on that exam would be a random variable. It would be a random number. And so kind of before I look at it, I don't know. So we want to model these phenomena. And so the way that we do this in probability is that we define a distribution for X, or everything we want to know about X is compactly represented in the distribution. And for a continuous, generally, the distribution tells you how likely it is for X to take a given set of values, okay? And for a continuous random variable, what we have is this information, the information distribution is compactly represented in the so-called density function, okay? Or you might have seen it as PDF, probability density function. Okay, how many people have seen PDF density? Okay, so what is a density? Anyone wants to remind us? Yeah.
So I guess so. It depends on if it's continuous or discrete.
It's continuous. Let's say it's continuous. Yeah.
The PDF could be seen as like the y value under the distribution where f of x sums up to 1.
So f of x sums up to 1. So it's the function, let's say, of x. It sums up to 1. Basically, in this case, it would be integral. But what is the meaning of f of x? Kind of is written. So if you've seen in physics, density, what does density mean? It's some quantity per unit length or volume or area. Okay, so it's something like that. So what is probability mass of probability density function? The name is on it, yeah.
That's for a specific x value. It tells you how much how tall it is. But like it's usually 0 because it's
right. Okay. So if you want to make it more precise, it doesn't give you itself the probability because it's density. So if you multiply it by some length, so if I multiply f of x by dx, let's say the length of the interval, a tiny interval around x. Okay. So density times the length would give me the probability. Okay. And for a given x, you're right. So for formality, we need to like look at an interval, like tiny interval. And so f of x dx would be the probability that lie on in an interval like x and x plus dx. What usually you do is that you plot this f of x, and rather than infinitesimal intervals, you look at macroscopic intervals, let's say a to b. And if you add up these probabilities, so each like little tiny interval here from x to x plus dx, let's say, if I look at the tiny interval, roughly the function is constant. And so f of x times dx is like the basically the area of this rectangle. Okay, so fx times dx will give me the probability, and when I add them up over the interval, it gives me the probability over this whole interval. So the probability that x lies in the interval is basically the integral from a to b. Basically, we sum these little rectangular areas. And so you've seen this in calculus that if you add them up and if the length of the intervals goes to 0, this would basically converge to the integral. So basically, you're summing the probabilities over these whole intervals. And so this is the relation between the density function and distribution. So the probability that x belongs to an interval is just integral from a to b f of x dx. Okay, so this is the probability and a tiny interval near x, and we add them up. That's the meaning of the density, right? Something that you integrate to get the probability. And if you've seen it in physics, the mass density you integrate to get the mass. Light density, so you could get integrated to get the volume of the light, density of the light. Okay. And because the random variable, the probability that it's somewhere on the real line is 1, so when you integrate the whole, like f of x over the whole real line has to add up to 1. Okay, so that tells you that the probability that x lies somewhere is 1. And because this time, so the length is positive, and this is some infinitesimal probability, f of x has to be positive. All that. Okay. Any of this kind of rings a bell? Questions? You're not going to use the concept as much in this course, but I just wanted to remind you, you start from a random variable, let's say a continuous random variable. You want to describe the distribution. Distribution basically gives you a rule to assign probabilities to these events. The fact that x belongs to A and B is an event, and you want to assign probabilities, and the density gives you a way to do it. So you integrate it over a set, and it gives you the probability that the random variable lies in that set. Does it make sense? Okay, no questions. So now, what is the expectation? The next concept is the expectation. We have the random variable, we have the PDF. How do you define the expectation for random variable? The expectation. Anyone remembers what the expectation is? Expected value, yes.
No, x dx.
Okay.
X f of x dx.
Okay, integral x fx dx. Correct? So what is the meaning? So what does this mean? This is just a formula. Anyone wants to interpret the formula? Yes.
It's the sum of each random variable weighted by its probability.
It's the sum of the values a random variable takes, weighted by the probability, yes. So if this was a discrete random variable, you would have like something like xi and then pi rather than the integral. Here, this is playing the role of the probabilities. It's the probability that fx dx is the probability that I'm in a tiny interval near x and times the x value, and then I average. So it's a weighted average of the values that the random variable takes, and the weights are the probabilities. The more probable ones have higher weights. In a sense, it's the center of mass of the distribution, where the mass is the probability. Okay. So if you have, let's say, exam, the PDF of the exam grades, you look at the bulk, and usually, like, this is where the center of the mass is, like where the thing takes peaks, and so that would be, say, 75 could be that. And I mean, if you have exams, the support would be kind of between, let's say, 0 and 100. So usually you actually see something bimodal. If you've taught a course, you'd see like something like this. In this case, actually, it would be like maybe somewhere here. But if things are unimodal, you get something like that. Like usually the bulk of the near the bulk. So it tells you where basically you can balance things. So if this was mass, you put a wedge under that, it would just doesn't move. Okay. It's the center of mass in physics, or basically expectation or mean probability. Does that make sense? It wouldn't be here, for example. It's somewhere in the middle because you're taking weighted average. No questions. So this is another interesting formula which says that if I want to compute the expected value of a function of x, expectation of g of x, rather than integrating, I have to calculate the probability mass function. Say PDF of g of x, let's say this was y. I would have to compute based on the definition y times f of y dy. So you need to go from this density of x, if you know it, to the density of y, and then you use the formula. It's just a weighted average. But then there's this result in probability that says you don't need to compute the density, you just calculate integral of g of x, f of x dx. So you integrate g of x against the density of x, and it gives you the expectation. This is very useful. We're not going to use it much, but a consequence of that we're going to use a lot. So that fact, I'm not going to prove it here because it took a long time in the morning course. So just you're welcome to look at that later. But the consequence is the linearity. So if I have, you can imagine this is a function g of xy. This could be more general than a single variable. So this is a function of two random variables. It turns out to be linear in this case. So alpha and beta are constant. So alpha x plus beta y is a linear combination. It's a linear function, and then as a function of x and y, it's a linear function. So if I want to take the expectation, you can use this formula to argue that it's equal to alpha expectation of x plus beta expectation of y. So it's the same linear combination but applied to the expectation. Another way of saying that I can pass expectation through, and then you'll either pull out the coefficients and pass it through the sum. Is this property familiar to people? Linearity of expectation. It's the most important property of expectation, along with monotonicity, which we're not going to use. Is it clear to people? We're going to use this a lot. Frequently used in this course. So alpha and beta have to be constant. They can't be random. Okay. The only thing random here is x and y. So for example, expectation of x minus y is expectation of x minus expectation of x. Like x1 minus x2 would be expectation of x1 minus expectation of x2. Here alpha would be 1, x would be x1, and then beta would be -1, y would be x2. Okay. And then I can extend this. For example, I can say, for example, something like, or I can write, let's say expectation of 2x1 minus 3z, this z is also another variable, plus 2y. Okay, let's say x. So if you want to apply the linearity of expectation, what would happen? Expectation x and z and y are random variables. Anything? Or anyone? Does it apply here? Linearity? Yes.
2 times the expectation of x is 3 times the expectation of z plus 2 times the expectation.
Great. Okay. So you guys know this. What was your name, by the way?
Correct.
Grant?
Yeah.
Okay. If you, again, state your name would be great because I've forgotten. You have to reinforce it for me to be able to reply. As you can see, you can extend it to general linear combination. It doesn't have to be two. Is this clear, people? Just pull out the coefficients and pass the expectation through the sum. Okay. So we'll come back to the expectations, like one of the most important quantities. The other important quantity that the statisticians really love is the variance. Okay. So what is the variance? Well, the formula is given there, but so you look at x, a random variable, the variance is you take the expectation of x minus mu is its mean squared. Okay. And you have this alternative formula here. Expectation of x squared minus the expectation of x squared. Mu here is the expectation of x. So the question is that what does it mean? What does the variance tell you? Kind of says on the slide. Anyone? Okay, I'm gonna draw a picture. So I have a distribution, let's say this is the mean, and I may have another distribution that has the same mean. So two distributions can have the same mean. So the mean of this is also that. Okay. The mean uniquely doesn't specify the distribution. So which one of the two distributions here is, so these are the PDFs. Which one has a lower variance? Which one has a higher variance? Yes.
There is another spread, so.
Purple one has a lower variance. Yeah, so it's a measure of the spread. So how far away you're from the mean. So you can see from here, you compute these deviations of x. So let's say if mu, this is also mu. This was x, for example. The deviation from mu would be this part. And so you square it, and then as x varies, you kind of average these out. Okay, so you take the average of the spread of x from the mean, and because you square it, nothing cancels out, so you get just basically the average deviation squared from the mean. Okay, and so if the distribution is really concentrated near the mean, the variance would be small. If it's like flat, so the blue one has higher variance. Plot another one. So this really diffuse one, this has the largest variance. Okay, high variance, low variance. Okay, it's a measure of how peaked the distribution is near its mean. Okay, so you can know more about the distribution by knowing both the mean and the variance. Just given the mean is usually little information. It's more deterministic in a sense. The random variable that has lower variance is more deterministic. You can figure out where it is more accurate. Another way of saying it is a measure of uncertainty, or in finance is a measure of risk. How much you don't know. Any questions? Hopefully it's clear. The variance. If you're statisticians, by this time you should have seen the variance, and you'll see the variance more. It's going to become your best friend at some point. And the more interesting thing is the covariance. The covariance of two random variables x and y is defined like this. So it's similar to the variance, but it involves two deviations. So I have x and y. I look at the deviations of x from its mean, and then y, the deviations of y from its mean, and I take the product, and then take the expectation. So it's the expected value or weighted average of this product. And if you expand and simplify, hopefully you've seen this has this other alternative expression. So what does this one mean? What does the covariance measure? There's no hint here, so you have to recall. What does the covariance measure? Yes.
So it shows us how the relationship between the variables.
Yes. So maybe can you expand on it a little bit?
It shows us basically the variables go up together or down together.
Okay, great. So it shows whether they go up together or go down together, or whether they move together, basically. They can measure co-movement or co-variation. So the thing to note is that, for example, because it's a product, it can be positive or negative, this quantity. It's a random quantity. And this would be positive if either both of them are positive or both of them are negative. If one is positive, the other is negative, the value would be negative. Okay, so the covariance is high because you take the expectation. If the majority of the time, the sign of these two are the same. If the deviation of x from y is, in an instance of the experiment, is high, then the other one is, sorry, positive, the other one is positive as well. So if both are to the right of their mean at the same time, or to the left of their mean at the same time, often, then the covariance will be positive. If one is on the one side, so this is one, let's say x, this is the distribution of x, and maybe this is the distribution of, this is, let's say, expectation of y. This is expectation of x. So x is here and y is here. I don't know, just it's random, but when I find x here, more likely I find y above its mean as well. Or when I find x here, I find y below its mean as well, most of the time. Then the covariance would be positive. If it's the other way around, so when I oftentimes when x is above its mean, the other one is below its mean, then they go in the opposite direction. So roughly you can say above mean means big, below mean means small. Okay, so if x is big and y is small, then most of the time it's like an average quantity because some cancellations occur. But this would be negative if the opposite happens. And if both of them are large at the same time or small at the same time, then the other, like it's going to be positive. So it tells you, it's summarized here. It's a product when x and y are on the same side of their means, and negative when they're on the opposite side. So covariance positive means they tend to move together. Covariance negative means they move opposite directions. Often, it's like on average. And covariance zero kind of means, I mean, usually you say no linear association, but really they're kind of, you can't tell if it's one is above the mean, there's no relation to the other one being below the mean roughly on average. It's like not the entire, it's a form of dependence. It's a measure of dependence a bit more generally, and it's actually measures the linear dependence in a sense. So I'm not going to go into that much, but if covariance is zero, the two variables are called uncorrelated. So kind of, if you know something about whether x is large or not, you can't say much or anything at all about y being large, just a little bit of caveat. Is this kind of clear, kind of sort of seeing this idea? It's not trivial. Quantity, we're not going to worry too much about the meaning, but it comes up. Okay, and when we calculate the variances, we can spend a lot of time discussing measures of association or variance. But I'm hoping that we've seen this in maybe 100B course at some point, or we'll see it later. This course is not about measure of dependence. It's about a little bit of measure of dependence via the linear model, but and this is good enough for a reminder. It's this. Okay? Questions? Comments? So if you look at this result or the definition, covariance of x and x is the same as the variance of x. Okay, so variance of x is really covariance of x with itself. There's also something called the correlation coefficient, which anyone remembers what it is? Correlation coefficient. Or correlation. Anyone else on this side? Maybe this side. On the back, correlation coefficient. I'll take anything as yes. Okay. Right, but how do you define this? Remember? Is it the same as covariance? Yes. It has the same flavor as the covariance, but what is the difference? Yes.
Covariance over new variances.
Yes, close. It's like the covariance divided by the square root product of the variance, product of the square root of the variance or the standard deviations really. So square root of the variance is standard deviation. So you just normalize it. It's a normalized measure. So the good thing about this is it's invariant to scaling. So if I scale x by a factor of 2, let's say, the covariance, as we'll see, is going to scale by a factor of 2, but this is invariant. This is insensitive to the measure of like to scaling variables. And this is going to be between -1 and 1. This is sometimes called Pearson correlation. Or correlation coefficient. And so the fact that it's between -1 and 1 is similar to the fact that the cosine theta that we did, like if you remember, you had like the inner product divided by the norms. That's the cosine of the angle between two vectors. This is very similar, but for random variable. So in fact, you can think of the covariance of x and y as an abstract inner product. It's like an inner product between two random variables. It has a lot of properties of inner products if you think of the random variables as vectors. And so this would be like a norm of x. This would be like a norm of y. I mean, I'm not going to dwell too much on it, but by similar Cauchy-Schwarz argument, this is going to be always a -1 to 1. And so they're going to be uncorrelated if covariance is 0 or equivalent correlation coefficient is 0. And the most associated they are is when this is either 1 or -1. If it's 1, they're highly correlated and in the positive direction. If -1 means they're oppositely correlated. When one is up, the other is down, and vice versa. Okay, have people seen this? Most likely you've seen it. 100B. Today everyone seems to be tired. See it, right? Okay. If you haven't seen it, just or you forgot, maybe just review the basic probability book and you'll be good. So the most important property of covariance operator is its bilinearity. It's similar to the linearity of expectation, but here the covariance has two arguments. So bilinearity means it's linear in each argument. So if I want to compute the covariance of a linear combination of two random variables here, x1 and x2, I have alpha1, x1 plus alpha2, x2. Alpha1 and alpha2 are constants. If I want to compute the covariance of this with y, I can go through the formula, but it turns out that once you write down the formula, it just expands like this. I get alpha1 covariance of x1 and y plus alpha2 covariance of x2 and y. And so basically, you can pull out the alphas and then pass it through the plus as if it was like an expectation operator. A bit more generally, I mean, it's linear in both, so you can do a little bit more with it. So for example, a covariance of alpha1 x1 plus alpha2 x2 and let's say 2y minus z. What happens is that I can distribute it. Let's say, okay, I'm gonna maybe do a simple thing. Too much. So what happens is, we'll see this later. Let me do it later on the example. So what happens is you do, if you want to see what it does is that you can treat it as if you're multiplying two products. So to see what this does is like alpha1 x1 plus alpha2 x2. If I multiply by y, I get alpha1 x1 y plus alpha2 x2 y. And I just replace this with covariance of x1. This is like a mental exercise. So it behaves as if you're multiplying regular products. You just replace these with the covariances in the end. And so, for example, if I do covariance of, or the more general formula is this, okay? If I have the covariance of the sum of a bunch of random variables, let's say AI, XI, AI is our coefficients here. And then another sum of a bunch of other variables, Bj is the coefficient and Yj is another set of random variables. So the first one is a linear combination, and the second one is a linear combination. The covariance is linear in both, so I can distribute. So you get something like this. So for example, you get A1 x1 plus A2 x2 and B1 y1 plus B2 y2. I can treat this is for 2. I can treat it as if I'm multiplying A1 x1 plus A2 x2 and B1 y1 plus B2 y2. So just multiply out, it would be like a1, b1, x1, x2 plus a1, b1, x1, y1 plus a2, b1, x2, y1 plus a2, b2, x2, y2, and then you go through and just replace these with just covariances. x1, x2, okay, covariance of x2, y1, covariance of x2, y2, and this is really going to be covariance of, I mean, what we have above there. Okay, so this is the easiest you can understand what bilinearity means. Because the product is also bilinear, just you expand and you get just a1, b1 covariance of x1, x2, and a1, b1, sorry, yeah, a1, b1 covariance of x1, y1, and then a2, b1 covariance of x2, y1, and then a2, b2 covariance of x2, y2. Does it make sense? I can't explain it easier than this. Okay. Are you seeing bilinearity of covariance? This is going to be very useful in this course. Okay. Seeing it or not? We're going to do some exercises and you'll see. So the particular choice of the second one, if I choose it to be the same as the first, I get the variance. The variance of the random variable is the covariance of that random variable itself. If I specialize to this special case, if you expand, you can see that just because this, I mean, if we expand this is just going to be the variance, and then you get this formula for the variance. So the reason why this works is because I have to do, I'm going to do J here. We need to do the second index has to be different, otherwise we're going to get confused. So covariance of sigma I, AI, xi, and then sigma j, AI, aj, xj. So if this is z, this is the same z. I just changed the indices to be different because I want to use that result. So I'm taking the covariance of z itself, so that would be the variance of z. So I can use this formula, and if I expand, I get the variance of z basically is summation ij, ai, aj covariance of xi, xj. So this gives you a very general formula to compute the variance of a linear combination of random variables without any assumptions. Okay. Sounds good? Most likely not. So for this reason, you're going to see a lot of examples. Any questions? This is like the abstract version. If you're good at math, you would like this. If you're not, you're going to get good at math by the end of this course. Okay. Once you look at this, it clicks. Okay, this is perfect. I can now use. So to see all in action, let's do an example. X1, X2 are random variables. We have variance of X1 is equal to variance of X2. Variance of X2 equal 1, and then the covariance is some number, which I'm just representing as rho. Let's do symbolically. Okay. We want to compute the variance of x1 minus x2 and the covariance of x1 minus x2 and x plus, sorry, x1 minus x2 is one variable and then x1 plus x2 another. We want to do these two. So let's do the first one. So anyone wants to help me write down the variance of x1 minus x2? I'm going to give you a hint. You write this as the covariance of x1. We can use that formula, but I mean, if you don't remember the formula, you don't have to remember. Like, just remember that covariance is bilinear, but just that single word is enough. The variance of x1 minus x2 is the covariance of x1 minus x2 with itself. Now, what is the next step? Anyone from that corner of the room wants to? That's too close. But let's see if anyone volunteers. Yes.
You expand it. See the
Bilinear, yes. So how do you, I mean, maybe you can help me write it. Right. What would I get?
yeah, oh, X1, X2, X1.
Sorry, maybe slower. The first one is cov x.
X1,
Right.
and you get minus X2.
Sorry. Yeah. Minus covariance of x2. Yes.
Or but the second one would be covariance of X1. X2.
Covariance of x1 and x2. Yeah. So this would be like this term. x2, x2. Is that correct? Anyone wants to check? So it's like as if you're doing the product and we just replace the product with the covariance. So you get covariance, the first term is covariance x1, x1, and then minus, I guess we are doing the first one, the second term of the first parentheses times the second, like the first term in the second parenthesis. So negative x2 times x1 is like negative covariance of x2, x1, and then the rest is similar. So we just, yeah, x1 times negative x2 would be the third, and then negative x2 times negative x2 would be just plus covariance of x2, x2. Okay. Does that make sense? So if you can multiply and expand this, then you can do that. That should be hopefully everyone. So what is the first term then? Now maybe you can chip in what you were saying. What was your name, by the way? Oh, yeah.
So
Talwick. Okay. Okay.
just
First term is P. No, this is like variance of x1, which is 1. As well as the second one, like the last term, sorry. This is going to be 1. How about these two? Covariance of x1, x2 is rho. How about the covariance of x2, x1? Right?
go
Rho, okay. Why?
equal to the covariance of X1.
Yes, so covariance is symmetric and you can see it from the definition. So if I compute the covariance of y and x, mentally replace the role of y and x in the definition here. So you get y minus expectation of y here, and then x minus expectation of x, the product. But the product is commutative, so you can just swap. It's just the same thing. Okay, so covariance of y and x is the same as covariance of x and y. So covariance is a symmetric operator. It's a symmetric bilinear operator. Okay, that's all it is, more or less. And so I get that. So if you do this, you get 2 minus 2 rho. So in particular, it's not 2. So it depends on the covariance. Because they're correlated, the variance, I mean, it's reflected in the variance. Something interesting, for example, happens if the rho is here is 1. Then the variance would become 0. So think about what happens. Think about what happens if rho is 1. Okay, I'll let you think about what it means for a random variable to have 0 value. So far, so good. Okay, so covariance of x1 minus x2 and x1 plus x2. Can anyone maybe, you guys can do it on your papers and then just tell me the terms. What should it be? It's very much similar to the other one, but the second one is plus. You get covariance of x1, x1. So the first one would be 1, and then covariance of x1, x2. Anyone wants to?
Plus mu minus 1
Plus rho minus rho, and then
minus
minus 1, which turns out to be 0. Okay, there's another surprising fact. So you just do it, you get covariance of x1, x1, which is 1, and then covariance of x1, x2, which is rho, negative covariance of x2 and x1, which is negative rho, and then negative covariance of x2, x2, which is negative variance of x2, which is negative 1. This turns out to be 0. So what does it mean? Sorry?
they're independent. X.
They are uncorrelated. Okay, so this is an important point. They're not necessarily independent, but they're uncorrelated. When the covariance is 0, the two random variables are correlated. It's slightly a lot weaker than independence, but it's a measure of dependence, but just let's say uncorrelated. Okay, and it's interesting because we started from two random variables that were correlated, and we constructed two random variables that are uncorrelated, and that could happen. Okay, if you construct carefully, like then you could, from uncorrelated variables, you can create correlation. Like, so from correlated variables, you can create uncorrelated variables. This is like whitening. It's like making things have 0 correlation. Questions? Whitening. In general, it's called whitening. Creating uncorrelated variables out of correlated variables. Okay. So we'll do this using the matrices, hopefully shortly, at some point. Okay, so this is so far review. Okay, hopefully you know this, maybe most of it. Now, what I want to do, questions? What I want to do is like extend these ideas to random matrices and random vectors. And they're not, I mean, the ideas are pretty straightforward. So let's start with a random vector. This random vector is just a vector, let's say y in Rn, whose coordinates are random variable. So y1 up to yn, and each one is a random variable. Okay, nothing fancy. It's just, let's say I have y1, y2, each one is a random variable, so we call it a random vector. Okay, and we want to define the expectation or the mean of this random vector. We want to define the mean or expectation. And the way to define it, what is the natural way to define the expectation? We want to define the expectation. How do you define it? Yes.
Take the expectation.
Yes, you just take the you just replace every element with its expectation. Natural thing to do. And so this is like the formal way. So this is just the general thing. And what it says is the expectation of y is just a vector, here a two-dimensional vector, whose ith coordinate is the expectation of the ith coordinate of that vector. Okay. The ith coordinate, the expectation of y is the expectation of the ith coordinate of y. It's just a mnemonic way of representing. Okay, nothing fancy here. And what is fancy is, so expectation of y would be just a non-random vector in Rn, the same dimension. And the fancy thing is this lemma, if A is a non-random matrix, m by n, and then I have my y, which is n by 1. This is y, this is A. I can multiply them, I get a new random vector, which turns out to be m by 1. Okay, so this is ay, m by 1. So y is random, is a random vector. A is deterministic, non-random. And because the inner dimensions match, A is m by n, y is n by 1, I can multiply, I get ay. So ay is now a new random vector, and both y and ay have expectations. And so the expectation of this new vector can be written as a times the expectation of y. Okay. In other words, I can pull out the matrix A. So this is a manifestation of linearity of expectation in vector matrix form. Okay. Matrix multiplication is a linear operation, and so it comes out of the expectation. We'll see examples of this. Is the meaning kind of clear? It gives you like a way to compute the expectation of ay in terms of the expectation of y by this usual product. So let me prove it so you can see how it works. Proof. If I want to prove this, I'm going to look at expectation of ay. And this is a vector. I'm going to look at the ith coordinate. Okay. That would give me a scalar. By definition, this would be expectation of the the ith coordinate of ay. Just that's the definition here up top. So now what we want to do is use the definition of matrix vector product or matrix product to expand this. So can you write this in terms of the entries of y and entries of a? Let me help you. You're looking at the ith row of matrix A, which has like a bunch of elements. And then I'm going to basically, if you recall, the ith row of ay is just the ith row of A multiplied by the first column or the only column of y. Okay, so I have to do this. You get multiplication entry y. So anyone can help me write a general formula for this quantity. Expectation. I'm going to put a summation here and then complete the rest. Yes. ij, yj. And then the limits of the sum. J from 1 to n. So j varies here, I is fixed. Yes. So what was your name? Kirsten. Okay. Anyone object to this? That's how, yes.
So J index is going along the row.
J would be along the columns because you're fixing a row,
Columns, yes.
right? And then the end column, yes. Okay. What was your name, by the way?
Alfred.
Alfred, okay. I'm gonna ask you multiple times till I learn, or I have bad memory, so good. So now what we can use here, or can we use here? Yes.
Linearity. Linearity.
Okay. How do you use it?
Split everything out to individual applications, like the aggregation of the I1, Y1, so it's expectation of
A1,
yeah, I1.
I1. So can you do it with the indices intact? Can you keep the summation, like do it abstractly?
That was that.
Like we have this formula. I don't want to unpack it. Like we can unpack it into a big like sum and then do it, yes, but I want to keep the format. What should I? Maybe let's try to see if you can do it. Okay.
And you put the expected inside the sum, so you do the sum of the expected values. So you just move this b inside the sum.
Yes, I moved this expectation inside the sum. I'm gonna put it inside if you want. Is that it? J. Can I do more? Yeah.
Since data is a constant,
Yes.
you could move it outside the expectation.
Yes. I'm gonna pull this as well out. So basically, if you want to simplify, you get j from 1 to n, aij, and then expectation moves inside. Just apply to yj. That's linearity of expectation. Just moves past the sum, past the constants, constant factors, and just you get this. Okay, so now let me call expectation of y, which is a vector, mu, which is another vector. It's just the same vector. Okay. So can anyone tell me what this expectation of yj is? Yes. Mu j, yes. By definition, this is the jth entry of this. And so what is now this summation? Aij mu j, j from 1 to n. Yes.
AU.
Very close. A mu is a vector. This is a number. I'm going to put brackets I. This is the ith element. Okay, it's very similar to this that we just did. It's just the ith element of ay. We now have ith element of a mu. Okay, good. So what did we prove? We proved that the ith element of expectation of ay is the same as the ith element of a mu, and this holds for all elements. So for all I, hence the expectation of ay is really a mu. So two vectors that agree on all elements should be the same. And a mu is really a times the expectation of y. Okay. Here's the proof. So just use the definition of the expectation of a vector, and then the formula for matrix multiplication, and the key is just the linearity. You can see it's just a rewriting of the linearity of expectation. Sounds good? So once you can do the proof, then you can already do the example. So we're not going to do the examples. You're going to see it in action a lot. Questions about this? Yes.
The ij, j, and the e, y. J is the definition of the vector. So you use definition vector. It's the definition.
So I use the definition of what the expectation of y is, or expectation of, so here is another random, so let's say this is z, this is a random variable. I'm looking at the expectation, sorry, a random vector. A random vector. The way to define this, we define the ith element of this quantity to be the expectation of, this is zi basically. Okay, that's the definition of the expectation of a random vector. This is the use of the matrix vector product formula. This is linearity of expectation. And then another use of the formula for matrix product. Okay, in the interest of time, we're gonna improve this a little bit, or just send this. Now suppose I have, this doesn't move, okay. Okay, now suppose I have a random matrix, A, maybe m by n. I want to define the expectation of A, and very naturally, the expectation of A would be a matrix whose entries are the corresponding expectations of the entries of A. So if the ij entry of A is Aij, then this matrix has ij entry expectation of Aij. Aij. And so we say the expectation of A is a matrix whose ij entry is the expectation of the ij entry of the original matrix. Okay, similar to a vector, nothing fancy. Okay, and then we get this result, which is saying that an extension of level 1, if A is random, in this formula, B, A, C, A is random, a random matrix, B and C are deterministic matrices. So these are non-random, B and C. And the dimensions are such that I can multiply them out. So I have three matrices, B, A, or A, B, C. A is the random one. So I multiply B, A, C. I get a new matrix, and it would be random. The elements would be linear combinations of the elements of A, the coefficients determined by B and C, product of elements of B and C. So because it's a random matrix, it has an expectation, as we define. And this formula is saying that that expectation can be computed in terms of the expectation of A by pulling out B and C out. This is similar to what we had. So in the vector case, you'd had, and let's not do it because it's confusing with A here. But this B and C are constant, and the linear transformation, we pull it, but pull it on the correct side. So you can't just do, for example, you can't say expectation of A times BC because even this might not be well defined. So matrix multiplication is a non-commutative order method, so they come out in the same order. Okay, just you apply the expectation to the middle. The proof is very similar. And then I'm going to skip it. It's an exercise for you to prove it. And we're going to just use it later. Does it make sense? It's a little bit harder to digest if you haven't seen it, but you'll see it in action. Just constant factors come out. Question? Okay, this is going to be repeatedly used in proving properties of covariance matrices and later driving properties of beta hat. By that time, you're going to be comfortable. You even remember the formula. You just do it. So just you'd kind of be very comfortable with this. Okay, so let's move on to what a covariance matrix is. So we defined the expectation of a random vector, defined the expectation of a random matrix. Now I want to define something related to variance of a random vector. So I have a random vector here. Entries are y1 up to yn. The thing with the variance is that each entry has a variance, but we also have pairwise covariances. So I have a lot more information than just the variances. So if I look at, let's say, y1 and y2, then I have this matrix, which is, I can form as, I have the covariance of x1 and x1, which is the variance of x1. And then I have covariance of x1, x2. And then I have covariance of x2, x1. And then I have covariance of x2, x2. And I can naturally arrange them into a matrix. If I have three variables, same thing. This is actually x1, x2. Let's see. Right. Which one?
Oh, no.
These are x1, yeah. So let's say y1, y2, y3. I'm going to have a matrix. I'm not going to write it. But we're going to have a matrix such that the ij entry would be covariance of yi, yj in general. Okay. And in particular, on the diagonal, I would have basically covariance of y1, covariance of y2, y2, dot, dot, dot. And then off diagonal would be covariance of these other things. So this is like third element, or third row on the first column would be covariance of y3 and y1 and so on. So you can write it down. So there exists a matrix that captures all the variances on the diagonal and all the pairwise covariances off the diagonal. So this matrix is called the covariance matrix of this vector. Okay, so if this vector is, let's say this is, if this vector is y, this would be the covariance matrix of y. So covariance matrix of y is an n by n. If it's a n-dimensional vector, the covariance matrix would be n by n. And the ij entry is really just the covariance of yi, yj. Okay. And if you expand it, this is just a definition. And in particular, if you look at the ith entry of covariance of y, you see that this is just the variance of yi. Okay. So I would get, for example, in this case, this would be like variance of y1, variance of x1, x2, covariance of x2, x1, and then covariance, let's say variance of y. Okay. Diagonals are the variances, off diagonals are the covariance. Or pairwise covariance. Sounds good. Have people seen the covariance matrix? Stuff here. Covariance matrix. Some people just write variance of, some write just variance of y. I'm avoiding that to not get you confused. So variance of a vector is like the same notation as when I write cov y, it just has a single element, and that element is a vector. I mean this. When I write covariance of yi, yj, and it has two scalars, it means the typical covariance. Okay, the notation is hopefully not confusing. If it just involves one variable, I mean, this might be a better notation because it matches. Oh, see, there's a cross covariance matrix as well. We're not going to use it, but I mean, this is my notation, but others use theirs. For a vector, there is a covariance matrix, which is of interest and captures all the things that we need. Right? Questions? So what I want to like now do is this matrix form. So this kind of allows us to do a little exercise to see what we have learned. So let mu be the expectation of y. So y is a random vector, mu is going to be its mean. And then let's define this y tilde to be y minus mu. This is a centered vector. And okay, before using that, what I want to prove is this result. The covariance of y can be written as the expectation of y minus mu times y minus mu transpose. So you look at this vector, and you multiply it by its transpose, and you take the expectation that gives you the whole matrix. This is a compact way of writing. Rather than entry-wise, we just do that. And you can see based on definition of what y minus mu is, you can see that it's really y tilde transpose. Okay. So why is that? Because anyone knows what the ijth entry of this matrix is? Or sorry, y minus mu times y minus mu transpose. If I look at the ijth entry, what would it be? This is really like a long vector times its transpose. It looks like this. And it gives me like a whole matrix here. So n by 1 by n gives me n by n. So what is the ijth entry of that product? If you want, I'm going to write it as y tilde, let's say we have y tilde transpose ij. This is a little bit easier. Yes.
Square of yi minus mu j squared.
Square of, can you say that again?
Y minus 1.
So y is, okay, so y is not a matrix. So y is, let me do this. Y is y1, y2 up to yn. And mu is also mu1 up to mu n. So y minus mu is really just a vector. y2 minus mu2. Now, can you tell me? Okay. yi minus mu I squared. So what happened to j? Yeah, I and j. So this would be if I and j are the same. So this is the I. So how about the Okay, yj minus mu j. So did you want to say something?
Oh, that was my answer.
Okay, that's your answer. Anyone else? Any objections? This is the correct answer. Okay, so if you have a vector u transpose, just if you do it once, you remember forever. So what is the ijth entry? If I do u transpose, it's like ui uj. Okay, it's very simple to remember. So this is a like a vector here to the y, it's like y tilde I, y tilde j. Okay, so I have this. So now when I take the expectation of this, what do I get? So what is this? Yeah,
So the covariance of y.
it's the covariance of yi, yj, because by definition, these mu i's are the expectations. So really, the ijth entry of this, if I take the expectation, is the covariance. And so because this is defined, the ijth entry is defined as this, you can see that it's equal to this quantity. Okay, and so it's really also expectation of y minus mu transpose, the ijth entry. Okay, so this is equal to this, and this is equal to this other expression. Why this inequality, that this equality holds is by definition of the expectation of a matrix. So the ijth entry of the expectation is the expectation of the ijth entry, and we calculated it turns out to be the covariance of yj, yi, yj. And so this matrix has to be, so this has to be just cov y, because its ijth entry is just what we want. Okay, so this is really like a simple proof of this fact. Okay, just write it down. It's not difficult. The more interesting thing is the second expression, which is similar to the alternative expression for the covariance, and I just want to do it as the last thing this lecture. Any question about this top calculation? It's a bit roundabout, but you look at the ijth entry of this. This is take the expectation, and it turns out to be covariance, but that's really the ijth entry of this guy. So the two sides have the same ijth entry, and so the matrices have to be the same. Okay, let me, in the interest of time, I'm gonna do this really quickly here. So if I do want to do cov y, I can expand. So I'm gonna use this formula. I'm gonna expand. You get y transpose minus y mu transpose minus mu y transpose plus mu transpose. So it just expanded that expression that we just proved using just, hopefully people know that y minus mu transpose is really y transpose minus mu transpose. So transpose commutes with linear operation. And just once you plug in, you multiply out, you get this expression, hopefully that I wrote. So now what is the next step? How can I simplify this? Linearity of it, yeah.
Let's distribute the expectation.
Okay, distribute, this is like linearity, expectation of y transpose minus expectation of y mu transpose minus expectation of mu y transpose plus expectation of mu transpose. Okay, any simplifications now that can occur? Linearity. What is this last term? I remind you that mu is constant. Yeah.
Just
Yes. Why?
it's all it's not random.
is non-random, so the expectation is itself, so mu transpose, this comes out. This we're gonna keep as is. How about this guy, for example? Expectation of y mu transpose.
You could take the mu transpose.
Okay, why? Non-random and it's linear, so it's an example of this formula. So here, like this is like mu, this is like y, this is mu transpose. Let's say this is identity. And so you get identity expectation of y mu transpose. Okay. When transpose comes out of the other side, you see it in action. How about this guy? Same mu comes from this side, and then expectation goes here. And really, I can replace, like, transpose also comes out. So I get this. So what is this, by the way? Expectation of y. Mu transpose. How about this one? Same thing, mu transpose. So what I get is the first term and then a bunch of mu transpose. So minus mu transpose, minus mu transpose, plus mu transpose. And if you take the account, it just, two of them cancel out, you get a negative mu transpose. So you just get this, okay? So prove this for me. You get the expectation of y transpose minus mu transpose. So do this as an exercise for yourself. Try to convince yourself this uses most of the things that we discussed. The rest stuff.
Yeah.